Hello everybody and welcome to the fourth instalment out of 10 for the chapter Differentiation in Edexcel's Year 13 Maths content. So we've seen so far how to differentiate logarithms and trig functions, and we've seen also the chain rule. Now we're going to have a look today at something called the product rule, which is almost as crucial as the chain rule. So before we get into that, let's have a look and get in the mood with some warm-up questions. So 4 to attempt here. My suggestion as ever is to pause the video at this point, jot these down, or just have a go in a rough book or your exercise books or files, and then press play when you're ready to see the solutions, and hopefully you've nailed them. So assuming you've paused the video and have tried these, let's have a look now at the solution to question number 1. So given that theta is small and measured in radians, use a small angle approximation for cosine of theta to show this is true. So that begs the question, what is this small angle approximation for cosine theta? Well, you need to know really that as theta approaches 0, so as theta approaches 0, we have that cosine of theta becomes very, very close to 1 minus theta squared over 2. Obviously, as theta goes towards 0, cos theta is very close to 1, but by including 1 minus theta squared over 2, that's a slightly better approximation than just simply 1. So including the second term makes the approximation even better. So what we're going to do now is we're going to substitute this in place of cosine theta into this equation here. So as theta approaches 0, what we're going to have is that 2 cos squared theta minus 8 cos theta plus 3, that's going to become approximately the same as 2 lots of this squared because cos theta is approximately 1 minus theta squared over 2, so that all squared, then minus 8 lots of cos theta, which is approximately 8 lots of 1 minus theta squared over 2, plus 3. So we just substitute in the small angle approximation for cosine theta here. Now if we expand and simplify, we just have to have faith it will drop out as long as you don't make any silly mistakes. So if we have a look at this bracket now, so this is a bracket squared. So if we square the first term, 1 squared is 1. Take the product and then double. So 1 multiplied by minus half theta squared is minus a half theta squared. Double that gives us simply minus theta squared. Then the last term all squared, theta squared is theta to the power 4, and the denominator 2 squared becomes 4. Then over here, minus 8 times 1, we can just do that straight away, that's minus 8. Then minus 8 multiplied by minus a half theta squared becomes positive 4 theta squared, and of course plus 3. Expand out this bracket now, so we've got 2 minus 2 theta squared. 2 times a quarter theta to the power 4 gives us half theta to the power 4, minus 8 plus 4 theta squared plus 3. Now at this point, you may well be slightly confused, because what we've got to prove here only is in term of a constant and theta squared, but here we have a theta to the power 4. But don't lose heart, just think about what's going to happen as theta approaches 0. So what we can just add in here is that as theta approaches 0, half theta to the power 4 is going to be absolutely negligible. So imagine theta is maybe 0.01. If you tried 0.01 and raised it to the power 4 on your calculator, well in fact I'll just show you now. 0.01, just for example, to the power 4 is absolutely minuscule. So if you just make a little note that as theta approaches 0, a half theta to the power 4 becomes completely negligible. So we can practically ignore it. So therefore, 2 minus 2 theta squared plus a half theta to power 4 minus 8 plus 4 theta squared plus 3, we can say is pretty much the same as, we can ignore this now essentially, and group together our terms. So in terms of theta squareds, we've got 4 theta squared here, take away 2, gives us the 2 theta squared like we needed. And then the constant terms, we've got a 2, minus 8, and plus 3. So 2 minus 8 is minus 6, minus 6 plus 3 gives us minus 3 as required. And so that's the full solution done. So indeed, 2 cos squared theta minus 8 cos theta plus 3 is pretty much one and the same as theta approaches 0 of the same as 2 theta squared minus 3. So we can now move on and have a look at warm-up question 2. So for question 2, we have a diagram of a circle centre O. Points A and B are of circumference like shown, and the area of the major sector, which is shaded, is 90 squared centimetres. So the shaded area is all of this, obviously. The reflex angle, in case you've somehow forgotten, which I very much doubt, just means the larger angle, which is more than 180 degrees. So this here is 5 radians. And we need to find the exact length of the minor arc from A to B, which of course is this portion here. So we're told this about the area of a major sector, so we need to remember the formula for the area of a sector. So the area of a sector, if the angle at the centre is given in radians, of course, is 1/2 multiplied by the radius squared multiplied by the angle. So if we apply this now, we're told that the area of that sector is 90 cm squared. So 90, just subbing in the values, equals 1/2 multiplied by the radius squared multiplied by the angle at the centre, where theta is the reflex one, which is 5. So 90 equals 1/2 r squared multiplied by 5. So if we now rearrange this, my suggestion would be to double both sides and then divide by 5. You should find that what we have after doing that is that 36 is r squared, and therefore r is 6 cm. We can now use that, as long as we remember the formula for the length of a arc. So length of an arc, where the angle is given in radians, is simply r theta. So if we sub in that r is obviously 6, and we also know AOB is 5 radians. So this angle here in red is 5 radians. So this angle here, where we want theta to be this one, I should have called it a different variable, I suppose, if you theta twice, where theta's meaning different angles, please forgive me. So this angle here, if this is 5 radians, and there's 2 pi radians in a complete full turn, this is going to be the other 2 pi minus 5 radians. So r theta means 6 multiplied by 2 pi minus 5, which in the given form we need, 6 multiplied by 2 pi is 12 pi, 6 multiplied by minus 5 is minus 30. So the length of the arc in the required form is 12 pi minus 30. Question 3 links to question 4 later. So first of all, what we have to do is to sketch the graph of equation y equals the modulus of 4x minus 3, stating the coordinates of any points where the graph cuts or meets the axes. So there's a couple of different approaches for how to sketch functions of the modulus. So the way I tend to do it these days is to just start with y equals mod x, the most basic function inside these modulus lines. So if we just start with y equals mod x, then what we'd have to do to transform it from y equals mod x to what this actually is, the correct order of transformations is very much the same as BIDMAS, but if we have anything inside brackets, or indeed inside the modulus signs, it works in the opposite order. So according to BIDMAS, what we'd normally do is we'd do the multiplying by 4 first, and then worry about the subtracting 3. But because all of this is inside the modulus lines, we need to deal with the x minus 3 first, and then do the 4x after. So it's opposite to BIDMAS because it's inside these modulus lines. A silly way of thinking about it, but it works for me. So first of all, what does the graph of y equals mod x look like? So we have this for y equals mod x, and then to go from this to y equals mod x minus 3, again, inside the brackets or the modulus signs is opposite to common sense. It looks like here we're subtracting 3 from the x-coordinates. Opposite to that common sense approach would be actually we need to add 3 to the x values. And so these red lines move 1, 2, 3 to the right. So this is the graph of y equals the mod of x minus 3. Finally, we need to apply this change here, which is going from x to 4x. Again, that 4 is inside the modulus signs. Inside works as opposite. So it looks as common sense would have it, but we're going to multiply the x-coordinates by 4. But actually what would happen instead, because it's inside here, we're going to end up dividing these x values by 4. Before we do that though, let's just think about where the x-intercept and y-intercept is for y equals x minus 3. Well, the graph of y equals x minus 3 has a gradient of 1. This point here would be where x equals 3, because 3 take away 3 is 0. And where x is less than 3, this line here is the line y equals 3 minus x. And so this y-intercept will be 3. And so both the y and x-intercept, or where it touches the x-axis at least, are both the value 3. Then, like I say, to go from the red to the blue, rather than multiplying the x values by 4, we're going to divide them by 4. The y values are unchanged, so this y-intercept will stay fixed at 3, but this x value here at 3 will be divided by 4, so this will become 3/4. So finally, the graph of y equals mod 4x minus 3 is the y-intercept 3, and down here that's going to be 3/4. But now I'm going to use this graph to help us to solve question 4. So question 4, using our answer to question 3, or otherwise, but we're going to use our answer to question 3 because that's the best way of doing it, find the complete set of values of x for which the modulus of 4x minus 3 is greater than 2 minus 2x. So let's return to our answer from question 3, the graph. So the graph we had is y equals mod 4x minus 3, like so. Now what we're going to do is plot the graph of y equals 2 minus 2x. So from GCSE, the graph of y equals 2 minus 2x, if I think of this as minus 2x plus 2 instead, that's going to have a gradient of minus 2, and it's going to cross the y-axis at 2. So it's going to go through 2, and it's going to go through here, where x is 1. So it's going to go y-intercept of 2, and cross the x-axis when x is equal to 1. So this graph I'm going to add in on red is going to look like so, and that's the graph of y equals 2 minus 2x. So to solve this, we need to find the critical points where the red crosses the blue, or vice versa. So where are these 2 points here located? So first of all, what we need to consider is where this line here with positive gradient crosses the red line, and then consider where this line with negative gradient crosses the line y equals 2 minus 2x. So we need 2 points, this one and that one, like so. So let's just think about solving this one here first, this purple one. So the purple point is going to be where this red, 2 minus 2x, is the same value as the blue, which is 4x minus 3. So when is 2 minus 2x the same as 4x minus 3? Well, if we add 2x to both sides, we get 2 equals 6x minus 3. Then add 5 to both sides, gives us 5 equals 6x. Therefore, dividing by 6, this critical value for x is 5/6. Now, if you think of this one over here, where it becomes 0, the modulus function then inverts itself. So if this one here is y equals 4x minus 3, beyond the critical point where it would have become negative, it then reflects, and so this line here is y equals minus all of 4x minus 3. In other words, this line here is the line y equals minus 4x plus 3. So next, what we need to do is to solve when minus 4x plus 3 is the same as this red line, 2 minus 2x. So when is 2 minus 2x equal to minus 4x plus 3? So now if we add 4x to both sides to solve this part of it, we then get 2 plus 2x equals 3. Then subtract 2 from both sides gives us 2x equals 1. Finally, halving both sides, we have x equals 1/2. So the blue, which I've obviously highlighted in this yellow, the blue part is greater than 2 minus 2x. For this region here, where x is less than 1/2, so all the way down here, and also where x is greater than 5/6. So therefore we can conclude and say 4x minus 3 is greater than 2 minus 2x for when x is less than 1/2, so it's half where x is less than that, so it's that bit, unified or joined with where x is greater than the line, the point, 5/6. So that's the solution set in set notation for the solution of the values of x, which satisfies this inequality. Now let's have a look at the main part of this lesson, which is going to be the product rule. So, what is the product rule? Well, it allows us to differentiate functions that are composed of the products of two or more functions, which we'll see later on. As with other mathematical formulae or results, there's different ways of writing it down, essentially. So the product rule can be written in multiple ways and notations. So the main three are as follows. In dy by dx notation, if y equals uv, where u and v are both functions of x, then dy by dx is u multiplied by the derivative of v plus v multiplied by the derivative of function u. In function notation, if y is ux vx, dy by dx is uv dashed plus vu dashed, or very simply, this lazy way, which is my favourite, probably says more about me than anything else, uv all dashed is uv dashed plus vu dashed. The product rule allows us to differentiate functions comprised of products of two or more constituent functions, like I've said earlier, and this is a powerful method when differentiating many complex functions. But first, let's just see and sort of prove to ourselves if it sort of works and is consistent with what we knew before using a carefully constructed example. So here, what I've suggested we do is we differentiate using the product rule and then differentiate without it as normal, if you like. So let's pick y to be a function that's a product of two other functions, u and v. So the function u is 3x squared, the function v is 12x plus 4, so therefore y of x is ux times vx. So for part A, what we're going to do here is we're going to write y of x entirely in terms of x by finding the algebraic product of ux and vx. So u of x is 3x squared, vx is 12x plus 4. So what we can say now for A part 1 is yx, which is ux times vx, that's simply going to be 3x squared multiplied by 12x plus 4, because u is 3x squared and v is 12x plus 4, obviously. So then if it's just a case of expanding these brackets out, if we do that, then 3x squared multiplied by 12x, 3 times 12 is 36, x squared times x is x cubed, and then 3x squared multiplied by 4 is of course just 12x squared. So that's part 1. Then part 2, it now asks us to find dy by dx as standard, so just differentiate this now as normal. So part 2, if y of x is this, then simply dy by dx, bring the 3 to the front, multiply by 36, that's going to give us 108, lose 1 from the power, gives us x squared, and 12x squared differentiates to 24x. So that's what dy by dx is, as we know already from year 12 even. Let's now try this chain rule thing. So for part B, Let's differentiate u and also differentiate v. So we've got that u is 3x squared. We have that v is 12x plus 4. So u dashed, differentiate 3x squared gives us 6x, and v dashed, differentiate 12x becomes 12, and the 4 disappears. So for part 1, u dashed of x is 6x, and v dashed of x is 12. So then part 2, then find in terms of x, u v dashed plus v u dashed. So for part 2, u times v dashed, all we need to do here, if we set it out like this, with u and u dashed in line below each other, and the same for v and v dashed, we can use a little trick which I think is fairly handy. u v dashed, we just do these cross-cross, then add on these two cross-cross. So u v dashed is just simply going to be 3x squared times 12, if I can get my pen correct. So yeah, u v dashed plus v u dashed. U is 3x squared times by 12 plus v, which is 12x plus 4, multiplied by 6x. So 3x squared multiplied by 12 gives us 36x squared. And then over here, 6x multiplied by 12x. Well, 6 multiplied by 12 gives us 72. X times x is, of course, x squared. And then 6x multiplied by 4 gives us 24x. Then simplifying both bits, we've got 24x's and 36x squared plus 72x squared in total gives us 108x squared. So that's B part 2 complete. Then part C, it asks us simply just to compare the answers to part A and part B. So for part A, dy by dx was 108x squared plus 24x. Then for part B, we ended up with uv dashed plus vu dashed was 24x plus 108x squared. I don't know about you, but I'm pretty inclined to say these are one and the same thing. So what we can say first of all is A and B are the same. Therefore, what can we say about the value of dy over dx and u dv by dx plus v du by dx? We can say that, at least in this case, and actually in all cases, we have that if we differentiate uv, we get u dv by dx plus v du by dx. And of course, this is in fact the chain rule. So this just shows that the chain rule works in this particular case. So the leap of faith, as we'll see later, hopefully, will be convinced that in all cases it does hold. D by dx of uv is u dv by dx plus v du by dx. So let's apply it and get warmed up and fairly good at using this with some worked examples and practice. So first of all, we've got a fairly simple product here with worked example 1. So y is the function x cubed multiplied by the function sine x is my advice how to think of this. So let's set u as being x cubed, and let's set the function v as being sine x. So now if we apply the product rule to this, as long as we remember how to differentiate these functions, we'll then be fine. So if u is x cubed, u dashed will be 3x squared, and if v is sine x, then the derivative of sine is cos. So we can now apply this product rule and differentiate this product. So therefore what we're going to have now is dy by dx is going to be uv dashed plus v u dashed. It's not actually called uvu by anyone apart from me, but there you go, that's how I think of it. So u is x cubed, so I'm going to do x cubed and multiply that by the function v dashed, which is cos x. And then we're going to multiply, sorry, we're not going to multiply, we're going to add on what we get if we do v multiplied by u dashed. So the function v is sine x, so then we're going to add on sine x multiplied by u dashed, which is 3x squared. So we've essentially got it there. So if we just write this in a normal way without any brackets, we're absolutely fine. So x cubed cos x. But I'd probably be tempted to write the x squareds first, so then plus 3x squared sine x. And that's how it works. So let's try a slightly trickier worked example. That was worked example 1. The next one, surprise, surprise, worked example 2. But just before we get on to worked example 2, a little note about the slightly trickier problems we're going to encounter. So sometimes what we need to do is combine product and chain rules together. So the product rule can be used in conjunction along with the chain rule to differentiate functions that are functions of functions, whether those functions are also products of other functions or form a chain within themselves. So let's have a look at a slightly trickier one where it will make more sense if we just apply this idea. So worked example 2, differentiating products. So we've got two products here. We've got e to the 3x squared, which obviously, as you can see, isn't the most straightforward of functions in its own right. And the other one is the square root of 1 minus 3x. So if we term the first one, u equals u equals e to the 3x squared, and say v is the square root of 1 minus 3x. In fact, what I will do, I'll say v is 1 minus 3x to the power of a half, because the square root is the same as to the power of a half. So now we can apply the chain rule, but of course these functions are slightly trickier, to say the least, than what we had in worked example 1. First of all, if u is e to the 3x squared, I'm not going to labour this point. If you don't believe me, I want you to try the chain rule yourself. U dashed is going to be 6x e to the 3x squared. Essentially, to work out u dash, what we can do is differentiate the function of x, which is in the power, bring it to the front, and then we have e to the 3x squared as it is. So if you don't believe me, try it yourself, put u equals e to the some other thing and apply the chain rule. You should hopefully convince yourself that u dashed is indeed this thing here. Now v is slightly trickier. V is 1 minus 3x all to the power of a half. What I'm going to suggest we do here is we say v, let's make up another one. We've got u and v. Let's say it's equal to w to the power of a half, where w is 1 minus 3x. We can now use the chain rule on this. So like I say, it's the product rule, and now we're using the chain rule to get us to the final answer of it. So if w is 1 minus 3x, then we can differentiate v to find v dashed. So v dashed, which is dv by dx, we can do dv by dw, then multiply by dw by dx. So v in terms of w, v is w to the power of a half. So differentiate v with respect to w will give us a half w to the minus a half, and then multiply that by dw by dx. If w is 1 minus 3x, differentiate this, just simply gives us negative 3. And so therefore v dashed is going to be minus 3 halves w to the minus a half. W to the half means the square root of w. W to the minus a half is 1 over the square root of w. So this is the square root of w on the bottom, but w, remember, was 1 minus 3x. So therefore that's the v dashed here. So to work out v dashed, we worked out that using the chain rule. So now we can just apply what the product rule is. So f dashed of x will be u times v dashed, like we said earlier. Then we add to that u dashed multiplied by v. So uvu, u v dashed, so it's going to be e to the 3x squared multiplied by minus 3 over 2 square root 1 minus 3x plus v, which is 1 minus 3x to the half, basically the square root of 1 minus 3x, multiplied by u dashed, which is 6x e to the 3x squared. So we have u times v dashed, where v dashed is this thing here, then plus v, which is this, multiplied by u dashed, which is 6x multiplied by e to the 3x squared. So now if you just write this in a slightly neater form, we're essentially just done. So we've got 6x e to the 3x squared multiplied by the square root of 1 minus 3x. Then we can subtract from that minus 3 e to the 3x squared all over 2 lots of 1 minus 3x square rooted. And in my opinion, that's a slightly neater form to write it in. Don't worry too much about the form you need to write the solution in. The examiner will normally give you a massive hint in terms of how to write it. Like you'll see here, question 3, works example 3, is an adapted worked example taken from an exam paper. So, worked example 3, we've got this product here, e to the 4x multiplied by sine squared 3x, and we need to show what dy by dx is, and we're given the form to write it in as well. So let's just set it out in terms of y equals u times v. So the first product is e to the 4x, v is sine squared 3x. So u e to the 4x, v is sine squared 3x. So let's think of this step by step, applying the product rule. Well, if u is e to the 4x, we can fairly easily differentiate that. It's e to the kx, so the standard result, to differentiate e to the kx, the constant comes to the front. So we have a 4 brought down to the front, which gives us 4e to the 4x. Over here, though, v is again like a function within a function. So for v, I'm going to say let v equal w squared, where w is sine 3x. Then if v is w squared, dv by dx, basically v dashed, will be dv by dw multiplied by dw by dx. So dv by dw. So if v is sine 3x, sorry, v is w squared, differentiate v with respect to w, that will just give us 2w. And then if w itself is sine 3x, if I differentiate sine 3x with respect to x, that will give us 3 cosine 3x. So 2w multiplied by 3 cosine 3x. And then if we simplify this, we've got 2 multiplied by 3, which is 6. W, which is sine 3x, cos 3x. Therefore, v dashed is 6 sine 3x cos 3x, based on what we just worked out here. So, using this and just piecing it all together, we're gonna get our answer essentially. Just need to keep our heads and not be freaked out about how awkward this looks. So, therefore, dy by dx equals uvu, my silly way of saying it, u v dashed plus v u dashed. So u is e to the 4x, wrong colour, silly me, So e to the 4x multiplied by v dashed, which of course is this awkward thing here, 6 sine x times cosine 3x. We're going to add to that v, which is sine squared 3x, multiplied by u dashed, where u dashed is 4e to the 4x. And sine squared 3x was, of course, v. So, simplifying this and trying to get it into the same form as what we need, we're going to have e to the 4x multiplied by 6. That's going to give us 6 lots of sine 3x cos 3x times by e to the 4x. Then over here, we're going to have sine 3x multiplied by e to the 4x. Then we can section out the other 4 and the other sine 3x. And then we're nearly done. So if we write first of all, like it says, e to the 4x sine 3x, then we can factorise out, of course, the 6 cosine 3x from here. And then from here, the 4 sine 3x as well. And there we have it. So that's an example where it shows us the form it wants the answer to be in. Now let's have a look at the final worked example 4. So given that x is 4 sine 2y plus 6, find dy by dx in terms of x. So what we're going to do here is actually use the fact that dx over dy is the same as 1 over dy by dx. So first of all, we're going to differentiate with respect to y. So if x is 4 sine 2y plus 6, then dx by dy, sine differentiates to cosine, and this constant 2 will come to the front. So sine 2y plus 6 differentiated with respect to y will become cosine 2y plus 6, which of course is just 8 cos 2y plus 6. So therefore dy by dx will be the reciprocal of that. So dy by dx is going to be 1 over 8 cosine 2y plus 6. And now we can think about what y is in terms of x. So we're told here that x is 4 sine 2y plus 6. So let's just think about this separately. So if we divide both sides of this by 4, we see that x over 4 will be the same as sine of 2y plus 6. If we then perform arc sine on both sides, we then get that arc sine of x over 4 will be 2y plus 6. So therefore, if we subtract both sides, subtract 6 from both sides and then half, we can see that y is arc sine of x over 4 minus 6 all over 2. So if we now input this into this expression here, we'll have our solution. But here we would need to work out cosine of 2y plus 6. Here we worked out what y is. So now we've got y. What we can do is change this into 2y plus 6. So this is what y is. So now we can just multiply by 2 to work out what 2y is. So times both sides by 2. We get that 2y is arc sine of x over 4 subtract 6. But we want 2y plus 6, so if we add 6 to both sides, we're going to get our expression, which we can then use in here. So therefore, we're going to have that 2y plus 6 is exactly arc sine x over 4. So now, the final step, really, is to input that 2y plus 6, we can use that as arc sine x over 4. So if we switch 2y plus 6 with arc sine x over 4, it's then all in terms of x as required. So therefore dy by dx is 1 over 8 cosine of arc sine x over 4. So although that's a slightly awkward expression, we have answered the question as instructed, so we're done. We don't need to worry about anything else. We can now move on if it was an exam. That's the solution and that's the final answer. So now it's time for you to try some of these on your own. So my suggestion would be to turn to your books now, 242 exercise 9D, and to try 1, 2, question 3B, and then questions 6, 7, 8, 9 and 10. And as ever, check your answers regularly using the back of the book to make sure you're on the right tracks. And if not, let me know as soon as possible. So thank you very much for listening. As ever, I do hope you find some of this useful, and hope to see you soon in class, on the channel, on email, or in some form or another. So see you soon, and all the best from me.